Having covered magnetic flux density, which is basically telling us how strong the magnetic field is with its equation B equals F over L, it would be useful for us to look into that force more closely. In fact, the equation is often remembered as F equals Bil, F equals BIL. So, for a large magnetic force, we want a high flux density, a large current, and lots of length of wire. If you think about it, there is the flux density ready to exert a force on a moving charge. The more charge carriers there are, and the longer they are in the field, the greater the total force. Obviously, force also has a direction, so let's look at that. Take this wire. Remember the arrow, so an X here means the current is going away from you. The right-hand grip rule tells us the field is going clockwise around the wire. Now, imagine another wire here, also with a current going away from you. Its magnetic field is obviously clockwise as well, so in the middle here, the fields cancel out. Since field lines tend to spread out, the wires are pushed together. There is an attractive force. Or, just consider the second wire on its own in an external magnetic field. The left-hand rule has the field here going down, the current going in, so the movement will be to the left, which is the same result as we just got. The same arguments can be made for wires with opposite currents to show it is a repulsive force in that case. Another thing I want to cover in this video is an alternative equation that we will want to use when we are thinking about the force on small particles, such as an electron in a magnetic field. So if we start with F equals Bil, and then consider that I equals Q over T, that gives us the equation F equals BQL over T. Looking at that equation, notice how we have L over T. That's a distance divided by time, which is the velocity. So we can substitute L over T for V, giving us F equals BQV. And that is a really handy equation. Now you might be wondering why or where. Well, we are starting to investigate some advanced physics, and some of the most advanced physics happens in the particle accelerators like CERN, or when looking for the Higgs boson in the Large Hadron Collider. In those situations, we can control the magnetic field very carefully. So let's work out how much magnetic field we need. We know the charge on the particle. We also know how fast the particles are moving because we are the ones that made it accelerate to get to that speed. We need to know the magnetic field required to apply a perpendicular force that will accelerate the moving charge towards the center of the circle. This is the basics of circular motion, and the force needed is F equals mv squared over r. So we know Q, we know V, and we know F. Therefore, we can easily calculate the magnetic field required to keep the charged particle moving in a circle. Another great example of this is in the mass spectrometer, but we'll have another look at that particular device in another lesson video.